Now, question number 11, exercise 9.5. Differential equation is x plus y dy plus x minus y dx is equal to 0, where a boundary value condition is given as y is equal to 1 when x is equal to 1. X plus y dy plus x minus y dx is equal to 0. First, we will have to transpose this term to right hand side. So on the left hand side, we have x plus y dy, and on the right hand side, it becomes minus x minus y dx. Now transposing dx to this side and x plus y to right hand side, we have dy upon dx is equal to minus x minus y upon x plus y. If we open up this bracket, this minus will change the signs of these two terms. So we may also write it as dy upon dx is equal to y minus x, and in the denominator x plus y may also be written as x plus y because addition is commutative. X plus y or y plus x is the same thing. So let it be equation number 1. Now we have to make the substitution y is equal to ux. Let it be equation number 2. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. Now proceeding from this step, dy upon dx is equal to u plus x du upon dx. Now we have to substitute the value of dy upon dx as u plus x du upon dx in equation 1, and y is equal to ux. So with the help of equation 1, 2 and 3, we may write on the left u plus x du upon dx, and on the right hand side in place of y we have to write down ux. So we have ux minus x over there, and in denominator y plus x is there, so ux plus x. Now if we take common, x is common out of these two terms, so in the bracket we have u minus 1, and in denominator in the same way x is taken common and we have u plus 1 inside the bracket. This x is cancelled by this x, and finally we have u plus x du upon dx is equal to u minus 1 upon u plus 1. Now in this step we have to transpose u to right hand side. So on the left hand side we are left with x du upon dx, and on the right hand side we have u minus 1 upon u plus 1 minus u. Now taking LCM, u plus 1, we have u minus 1 minus u plus 1. Now x du upon dx is equal to, opening these two brackets, we have in the numerator u minus 1 as it is, and opening this bracket minus u will multiply both the terms. We have minus u square minus u divided by u plus 1. Now this u is positive and this u is negative, both are cancelled with each other, and we are left with minus 1 and minus u square. So we may take minus common out of these two terms. We have minus u square plus 1, or 1 plus u square is the same thing, and in the denominator u plus 1. Now we have to transpose this expression u square plus 1 upon u plus 1 to the left hand side towards u. The x and 1 upon x to the right hand side, we may rearrange the terms as u plus 1 upon u square plus 1 is equal to minus 1 upon x dx. This is variable separable form, and we have to integrate both the sides. Integral u plus 1 upon u square plus 1 du is equal to minus integral 1 over x dx. Now splitting them up, we may write this integrand as integral u upon u square plus 1 du plus integral 1 upon u square plus 1 du is equal to minus 1 upon x integral 1 upon x dx. Now proceeding from this step, here in the first integrand, we may write it as 1 upon 2 integral 2u upon u square plus 1 du. We have done so because to use the exact differential of u square plus 1. So if we assume u square plus 1 as t, we get 2u dx as dt. So simply we may write it as 1 upon t dt, and directly the integral will be log t, and t is u square plus 1. So directly we may integrate it keeping this algorithm in our mind. That's why I have multiplied numerator and denominator by 2, and I have written this expression as this. So in the next term, we have 1 over u square plus 1 du. This is directly integrable, minus integral 1 over x dx. So now it becomes 1 upon 2 log u square plus 1 plus tan inverse u is equal to minus log x plus c, where c is the constant of integration. Now transposing this log x to left hand side, it becomes positive, and we have 1 upon 2 log u square plus 1 plus log x plus tan inverse u is equal to c. Multiplying both sides by 2, we may write this equation as log u square plus 1 plus 2 log x plus 2 tan inverse u is equal to 2c. Now this 2 can be written in the power of x by using logarithmic property. So we have log u square plus 1 plus log x square plus 2 tan inverse u is equal to 2c. Now simply log m plus log n is equal to log m into n. So using that property, we may write these two terms as single term log u square plus 1 into x square and plus 2 tan inverse u is equal to 2c. Now proceeding from this step, now since from equation number 2, we have y is equal to ux, and simply from this, if we find the value of u in terms of x and y, we get y upon x. So now replacing in this equation, u by y upon x, we get log y square upon x square plus 1 into x square plus 2 log 10 y upon x is equal to 2c. Log, taking LCM in this bracket, we have y square plus x square upon x square into x square outside plus 2 tan inverse y over x is equal to 2c. Now simply this x square will cancel this x square, and we have simply log y square plus x square plus 2 tan inverse y upon x is equal to 2c. Let it be equation number 4. Now this is the step where we need to find out the particular value of c with the help of this boundary value condition, which is y is equal to 1 when x is equal to 1. So since y is equal to 1 when x is equal to 1, putting in this equation, we have log 2, because 1 square plus 1 square, that is 1 plus 1 2, and plus 2 tan inverse 1 upon 1, that is tan inverse 1, that is pi by 4. So pi by 4 is equal to 2c. Now this 2 will divide this 4 2 times, and if we transpose 2 to right hand side, it will divide both the terms. So we have c is equal to 1 upon 2 log 2 plus pi by 4 plus pi by 4. That will be equation number 5. Now to find the particular solution of the given differential equation, we need to substitute the value of c, which we obtained as 1 upon 2 log 2 plus pi by 4 in equation number 4. So we get log pi square plus x square plus 2 tan inverse y upon x is equal to 2 into bracket is equal to 2c. So 2, and the value of c is taken from equation number 5. We have within a bracket 1 upon 2 log 2 plus pi by 4. So now opening the bracket, we have log 2 plus pi by 2. So we have log y square plus x square plus 2 tan inverse y by x is equal to log 2 plus pi by 2. And this is our required solution of the given differential equation. Now we are going to solve question number 13 from exercise 9.5 NCERT, and we have skipped 12th one because we have explained the question number 11, and 12th is very similar to 11th one. So that should be tried out yourself. So 13th one, we are going to start. So that is x sine square y upon x minus y dx plus x dy is equal to 0, where boundary value condition is given as y is equal to pi by 4 when x is equal to 1. So the given differential equation is, now dividing both sides by x dx, we get, in the first term dx will divide dx, so we get 1 outside, and if we divide the both terms inside the bracket by x, we have sine square y upon x is left in the first term, and in the second term we have y upon x minus y upon x. And in the second term, if we divide this by x dx, so x will cancel x, and dy upon dx, so we have plus dy upon dx is equal to 0. Now transposing these two terms to right hand side, leaving dy upon dx on the left, we have dy upon dx is equal to, on transposition this term becomes positive y upon x, and this term becomes negative minus sine square y upon x. That will be equation number 1. And now here we have to let y over x as u, which is simply y is equal to ux, as we have done before. Let it be equation number 2. So now differentiating with respect to x, this equation, we have dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. Now using equation number 2 and equation number 3, we have to replace dy upon dx by u plus x du upon dx on the left hand side in equation number 1, and on the right hand side we have to replace y upon x by u as we have assumed it in equation number 2. So replacing dy upon dx by u plus x du upon dx on the left hand side, we have u plus x du upon dx, and on the right hand side y upon x becomes u according to our assumption from equation number 2. Y upon x is equal to u, so on the right hand side we have u minus sine square u. Now transposing this u to right hand side, we have x du upon dx is equal to u minus sine square u minus u. This positive u and negative u are cancelled with each other, and we are left with x du upon dx is equal to minus sine square u. In this step, transposing sine minus sine square u to left hand side and x dx to right hand side, we have minus 1 over sine square u du is equal to, on the right hand side we have 1 over x dx. So this may be written as minus cosec square u du is equal to 1 over x dx. So this is variable separable form, so in this step we have to integrate both sides. Minus integral cosec square u du is equal to integral 1 over x dx. Now as we know well, integral of cosec square u is minus cot u, so minus and minus becomes plus, and simply we have cot u is equal to, and integral of 1 upon x with respect to x is log x, plus constant of integration is taken as c. So let it be equation number 4. Now from equation number 2, as we have assumed y upon x is u, so we have to replace here in this step u by y upon x. So we have cot pi over x is equal to log x plus c. Let it be equation number 5. Now in this step we are going to use boundary value condition to find the particular value of c. So using boundary value condition, y is equal to pi by 4 when x is equal to 1. So substituting in this equation 5, y as pi by 4 and x is equal to 1, so we have cot pi by 4 is equal to log 1 plus c. As we know well, cot pi by 4 is 1 and log 1 is 0. So We have 1 is equal to 0 plus c, or simply c is equal to 1. Now putting back c is equal to 1 in equation number 5, we get the required solution of the given differential equation. So we have got y over x is equal to log x plus 1, and this is our required solution. Number 14, dy upon dx minus y upon x plus cos sec y upon x is equal to 0, and the boundary value condition is given as y is equal to 0 when x is equal to 1. So let's do it. Dy upon dx minus y upon x plus cos sec or cosec, whatever you call it. Someone call it cosec or someone pronounce it as cosec. I think this is the difference between the British and US pronunciation of this word. And now we have to transpose these two terms to right hand side. We have, or there is no need to transpose this to right hand side. We may simply write it down as it is. Let it be equation number 1. And now we have to assume y upon x as u, or y is equal to ux. Let it be equation number 2. Differentiating equation number 2 with respect to x, we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. So using equation number 2 and 3, we may write equation number 1 as we have to replace here dy upon dx by u plus x du upon dx. So u plus x du upon dx, and then minus y upon x, which is taken as u in equation number 2. So we have to replace y upon x by u. So minus u, and plus cosec u is equal to 0. Here positive u and negative u are cancelled with each other, and we are left with x du upon dx plus cosec u. Now transposing cosec u to right hand side, we have x du upon dx is equal to minus cosec u, which may also be written as minus 1 upon sine u, because reciprocal of cosec is sine. Now transposing sine u to left hand side and x dx to right hand side, we have sine u du is equal to minus 1 over x dx. Now let it be equation number 4. Now proceeding from this equation, we may integrate both sides because these are variable separable, and this is the variable separable form. So integrating both sides, integral sine u du is equal to minus integral 1 over x dx. So integral of sine u is minus cos u, so minus cos u is equal to minus integral of 1 over x is log x, and plus c as a constant of integration, and let it be equation number 5. Now here in this step, first we have to replace u by y upon x as we have assumed it in equation number 2. So minus cos y upon x is equal to minus cosec x plus c. Now this is the step where we need to find the particular value of c for this boundary value condition. So since y is equal to 0 when x is equal to 1, substituting in this equation, we have minus cos 0 upon 1, that is 0, is equal to minus log x is 1, so log 1 plus c. As we know well, cos 0 is 1, so minus 1 is equal to, and log 1 is 0, so it becomes 0 plus c. So simply we have c is equal to minus 1. Now putting the value of c as minus 1 in this equation, we have to write down minus cos y upon x is equal to minus log x minus c. So multiplying both sides of this equation by minus 1, we have final required solution of the given differential equation, which is cos y upon x is equal to log x, which is minus 1, and that is plus 1. So this is the required solution of the given differential equation. 2xy plus y squared minus 2x squared dy upon dx is equal to 0. Now transposing this term to right hand side, we have 2xy plus y square is equal to 2x square dy upon dx. Now transposing 2x square to left hand side, it will divide both the terms. So we may write it as dy upon dx is equal to 2xy upon 2x square plus y square upon 2x square. Here in the first term, 2 is cancelled by 2 and x will cancel 1 power from denominator. So we may write this equation as dy upon dx is equal to y upon x plus 1 upon 2 y upon x whole square. Let it be equation number 1. And now we have to assume y is equal to ux. Let it be equation number 2. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. Now replacing dy upon dx in equation number 1 by the expression u plus x du upon dx with the help of equation number 3, and replacing y upon x by u, because by the assumption y is equal to ux, we have u is equal to y upon x. U plus x du upon dx. On the right hand side, we have to replace y upon x as u, so that is u plus half, and y upon x as u, so it becomes u square. Now this u positive and this u positive are cancelled with each other on opposite side of equality, and we have x du upon dx is equal to half u square. Now transposing u square to left hand side and x dx to right hand side, we have 1 upon u square du is equal to 1 upon 2 1 over x dx. Now integrating both sides, we have integral u raised to the power minus 2 du is equal to half integral 1 upon x dx. Integral of u raised to the power minus 2 is e raised to the power minus 1, u raised to the power minus 1 upon minus 1 is equal to half, and integral of 1 over x is log x, and plus c. So simply we have minus 1 upon u is equal to half log plus c. Let it be equation number 4. Now we have to replace u by y upon x, because we have assumed y is equal to ux, and by that relation value of y in terms of value of u in terms of y and x is y upon x. So if we replace u by y upon x, it becomes minus x upon y, and that is equal to 1 upon 2 log x plus c. We better make this equation number 4. This is the step where we have to find out the value of c according to given boundary value condition. So since y is equal to 2 when x is equal to 1, substituting in this equation, we have minus 1 upon 2, because x is 1 and y is 2, so 1 upon 2 minus 1 upon 2 is equal to 1 upon 2 log 1 plus c. Now log 1 is 0, so this term becomes 0, and we have simply c is equal to minus half. So putting c is equal to minus half in equation number 4, we have minus x upon y is equal to 1 upon 2 log x minus 1 upon 2. Now transposing 1 upon 2 to left hand side, we have 1 upon 2 minus x upon y is equal to 1 upon 2 log x. Multiplying both sides by 2, we have 1 minus 2 x upon y is equal to log x. Now taking LCM as y minus 2x is equal to log x. We may leave our answer over here, though we may write it in the different forms as using the definition of a logarithm. We may write this as x is equal to e raised to the power y minus 2x upon y. So this is our required solution. You may write this as if final solution or this. It will not make any difference.